We might already be close to becoming a star-building civilization, and you don't even know it. The reality is, for a civilization to build a star, it depends entirely on how advanced that civilization is. To achieve something like building a star, humanity would need to reach a level of civilization we can't even begin to imagine. But what does that mean? And how close are we to becoming that kind of civilization? And does it even make sense right now to create an entirely new star? How does a star form naturally? Well, G-type stars like our Sun are essentially giant machines that convert hydrogen into helium. The Sun alone contains about 1.46 octillion tons of hydrogen. That's 1.46 billion tons. But even something that massive had a beginning. Stars are born inside enormous clouds of gas and dust, made mostly of hydrogen, the original ingredient of the universe, leftovers from the moment it first came into existence. When gravity pulls parts of such a cloud together, it collapses into a denser and hotter core, a so-called protostar. It's basically a star embryo, and the heartbeat begins when the core temperature becomes high enough, around 18 million degrees Fahrenheit or 10 million degrees Celsius. That heartbeat is fusion. Under immense gravity, atoms move insanely fast. So fast, they collide and fuse together. Hydrogen merges into helium, releasing enormous amounts of energy. This is why a star appears to burn, but technically it doesn't. Fire needs fuel, heat and oxygen. We have fuel and heat, but there's no oxygen in space. So, stars don't burn. At least not in the way we think. They shine because of the light and heat released by fusion. And in the end, a star is a balance between gravity pulling inward and energy pushing outward. A burning star that isn't really burning at all. How could a civilization do this itself? The interesting part is we've been trying to trigger nuclear fusion for decades, or well, imitate it. Who else but NASA, and more specifically, projects like ITER, are working on this. Mainly hydrogen, but also other light elements are heated to extreme temperatures, causing them to fuse into heavier elements. Sound familiar? That's exactly what happens inside a star. The only difference is how we do it here on Earth. In stars, fusion happens because of gravity. On Earth, we use magnetic fields or lasers inside, what's called a tokamak reactor. This design already dates to the 1950s. First, an electric current is passed through the plasma, causing it to heat up. Then, high-energy hydrogen atoms are fired into it, almost like a supersonic laser beam. This pushes the temperature to insane levels. We're talking about 150 million degrees Celsius. But plasma that unstable doesn't just sit still. It needs to be controlled. Powerful superconducting magnets create an ultra-high vacuum, basically removing air entirely, just like in space. In fact, we're literally recreating space-like conditions. This keeps the superheated plasma contained, so we can continue experimenting with it. Okay, amazing, right? So today we can replicate the core process that makes a star a star. Problem solved, right? Well, not even close. Stars naturally have an enormous mass and gravity. Stars like our Sun are incredibly stable, maintaining a perfect balance between fusion and gravity. And it took millions of years to reach that perfection. Because plasma reaches temperatures of millions of degrees, all particles inside it behave like uncontrolled projectiles, shooting around at insane speeds. That makes it extremely difficult to keep the fusion process stable. Yes, we already have impressive techniques, but a true, fully functional fusion reactor still doesn't exist. We do have nuclear reactors, but those split atoms, which is called fission, which is very different from fusing them together into heavier elements. Because we are dealing with absurdly high temperatures, we need to get much better at stabilizing these conditions. But even if we manage that, there's another problem. Fuel. The Sun contains 1.46 octillion tons of hydrogen, like we said. And that's not exactly something we can just refuel somewhere or transport in tanks. Sure, we can produce hydrogen from water. By running electricity through water, we split oxygen from hydrogen and get the substance we're looking for. But we would need way more of it. We're talking about universe-altering levels of engineering, while we're still standing with our feet in the mud. So how do we know if and when our civilization could ever handle mining that much hydrogen and actually start manipulating the natural evolution of the universe? For that, we turn to the Kardashev scale. A star is a source of energy. Civilizations can exist in all shapes and sizes, from godlike beings manipulating entire galaxies to ants crawling across the ground. Life comes in many forms, but how do you measure how advanced a civilization is? According to Nikolai Kardashev, it all comes down to one thing: the use of energy. A group of beings living under a rock might just be discovering fire, while galactic demigods are figuring out how to reignite a dying galaxy. What they have in common is simple: they both depend on energy, but one is so far ahead of the other, and you can see that difference in the source of energy they use. Kardashev originally defined 3 types of civilizations. Many more have been added since, but this is where it all began. A Type 1 civilization can use all the energy available on its home planet. A Type 2 civilization can harness all the energy in its solar system. A Type 3 civilization has access to the energy of its entire home galaxy. And honestly, that scale is almost impossible to comprehend. So, which civilization could create a star? In principle, it's not even that complicated, at least not on the Kardashev scale. A Type 2 civilization can already harness the full energy output of its star, like our Sun. But a Type 3 civilization goes far beyond that. We're talking about access to all available energy sources in a galaxy, nebula, gas clouds, and even black holes. At that point, you're not just using space, you're actively engineering it. And that's so far beyond us, it's almost absurd. Right now, we're sitting somewhere around 0.70 to 0.75 on the Kardashev scale. We use energy from Earth, water, wind, sunlight. But we're not even close to using all the available energy, and we haven't figured out how to do it responsibly. Not that responsibility is technically a requirement on the Kardashev scale, but still, it would help. If we manage to cooperate and not destroy everything in the process, we could become a full Type 1 civilization in about 100 to 300 years. Type 2 is far less certain, but estimates range from hundreds to thousands of years, depending on how far our scientific understanding and capabilities evolve. And Type 3? Well, that's on the scale of millions of years into the future. So yeah, not exactly right around the corner. Is it worth it though? We've already managed to split the atom, and we're on the edge of recreating fusion here on Earth. Maybe, if we're lucky, we'll create a stable, non-burning form of energy and somehow cheat the Kardashev scale. Stars eventually evolve into white dwarfs and cool down for billions of years, and that alone is enough reason for a billion-year-old civilization to start getting creative. Maybe becoming an advanced civilization isn't just about technology, but about how far creativity and ambition can take you. Could we one day build a civilization that doesn't rely on energy and heat as we know it, but instead runs on something like dark energy, or taps into the deeper, almost interdimensional aspects of gravity? For now though, we live in an incredible moment. We have a stable sun, and we get to enjoy a world powered by it. A source of energy that will last for billions of years, so stable that we don't have to worry about it suddenly switching off.